Welcome back, function folks, for part two. And this should be, if all goes according to plan, the last video of the regular season. Later on, we'll be doing some playoff videos, both getting ready for the exam, but this is the last regular season video. And this is a weird one, and I'm going to have to ask you to be patient with this because you're about to be asked to do some strange stuff. This example, too, is actually modeling um, a real life phenomena. I'm going to show you a video of me sort of bouncing a spring up and down, and we're going to try and get an equation for it. That's the whole plan. But since it's a video of me doing this, there's video of me doing it. So you're going to have to stop and go back and forth between this video and the other one. And I don't know how you're going to do that, but hopefully you can manage. So as far as the note-taking part, I think I just jot down maybe a few notes, scribble a few graphs. You don't have to copy down everything you see here, but yeah, you're going to have to pause at times and go back and forth. So what you should do right now is pause and look for the first of the videos called Dampened Spring. All right, you watch the first video. That's the data right there that we came up with. And what we're going to do, because it kind of looks like a sine function, the second video, Dampened Spring 2, actually does the regression. There are the steps that I hit during that second video. So go ahead, you can watch that one. Okay, you've watched the two videos. Now, the weird thing is that you noticed in that second video, and that I sort of mentioned, is that the sine function isn't great, right? It actually looks like there's that first sine function. This was the one that the regression gave us. It's not great because what happens is the maximum heights are going down, and this is a little spreadsheet that I made up. Please do not copy all of these numbers down. That wouldn't make sense for you to do that. But the maximum heights are going down, which means what's changing is the amplitude's changing. That number right there is changing. It's going down. Our first instinct might be to say, maybe it's a linear function. It's just going downhill. But the thing is if that were to keep going as a linear function, it would keep going downhill, 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 to hit the ground and keep going down, 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 and eventually be negative, and that doesn't make any sense. What's happening is it's decreasing, but never quite being zero, right? It's getting closer and closer to an amplitude of zero. That sounds like an exponential decay function, and in fact, that's what I did. I went through and I put the amplitudes and their respective times into the Desmos or graphing calculator. I can't remember now which one I did. I'm not going to show you that, but I just did exponential regression and got a model for just the amplitudes. And so where I had 0.95 centimeters before, or 0.95 meters before, 0.095 I think that is actually from the video, I'm going to have this value now. So that's going to be the graph. There, I've replaced 0.095, 9.5 centimeters, with that function. And that's what I do in the third video. So you should pause this, and go back and watch this video. It's called Dampened Spring 3. Okay, so much better, and actually perfect, almost perfect. But it feels like we are leaning on the technology a lot. This function was a regression. This function was a regression. It feels like we've been working with these sorts of things all year. Can we not just use our skills from those sections to replace all this computer stuff? And in fact, yeah, we can. And I'm going to walk you through what we did. And you please don't write all this stuff down. Just absorb it. You can jot down maybe a few notes, but I wouldn't write down all this. So this is the brain or logic version, like using our skills. So for instance, for the exponential model, it looks like the first one, since at 0.6 seconds, the first amplitude was around 18 centimeters. So why didn't I start with 18 centimeters? That makes sense. I don't need a calculator to do regression there. Then how do I get the base? Well, what I can do is just figure out what the common ratio is. What is the base? What am I multiplying each time to get the next number? And so I did that. I went 0.12 divided by 0.178, and that was this number. And then I went 0.112 divided by 0.12, and I got that number. And then the next one was that number, and the next one was that number. And since this is a multiply thing to get the next number, it's a geometric mean again. We've seen this a few times. I can multiply these up and take the 8th root, and I got the base of 0.835. And notice that it's a little bit different than what the regression did, but still, okay, that's the decay value. It's 84% of its amplitude it's keeping. But what about the sine function? How do I get all this crud? Well, we're pretty good at this, right? In fact, remember, the period is just the distance between the horizontal distance between maximums. So from 0.6 to 2 was 1.4. From 2 to 3.3 was 1.3. And since I'm just adding each cycle, then this is a normal arithmetic mean. I add them up and divide by 8, and I get a period of 1.35. The first maximum is just right a little bit, right? The first maximum was right 0.6 seconds. So that's my phase shift. For vertical displacement, remember that was kind of like the average height, right? When it's bouncing up and down, the vertical displacement is the rest value or the average height. And I could have just taken all of the numbers from the calculator, added them all up, and divided by the number of numbers to get the mean, the overall mean. But instead, I just took the first maximum and the first minimum, added them up and divided by 2. It was a little bit lazy, but I got a vertical displacement of 0.961. That's different than the regression model, but still not bad. This is all fairly straightforward stuff, right? I mean, all skills we've done before. Really, we haven't sort of found the average of periods, but this kind of feels like what we did in our trig modeling assignment. We did some of this in our log function unit, and then that gives us this equation. Right? There's the amplitude that's decaying. There's our cos function, right? Because we started at a maximum. There's the phase shift, 2 pi over, because the period is here, right? And I can read that. There's my vertical displacement. And then I get the last video is me putting this in. That was all based on logic. So you should pause that and pause this video, watch that. And that's that, folks. So a word of warning, or maybe word of reassurance that the stuff in the homework's nowhere near this complicated. That I wanted to show you that we can do this sort of stuff in regression. We can put combinations of functions together to make our models quite complicated if we would like. The stuff in the homework is usually more like the Raging River example, where you just plot the data, pick the appropriate function, and then model it in some way, usually using technology, either Desmos or graphing calculator. And that's the end of regular season.